stop right now. The light entering your eye from Andromeda has been traveling for 2.5 million years. And Andromeda is, by cosmic standards, practically next door.
Subscribe, there's a new one every few days. Welcome to White Space. No rush, just the cosmos. There is a number that appears in almost every conversation about the cosmos, and yet no human being has ever truly understood it, not felt it, not held it in the mind the way you hold the weight of a stone or the distance to a house on the other side of the street. The number is approximately 9.5 trillion kilometers. That is a single light year, the distance light travels through empty space in 1 year, moving at 300,000 kilometers every second without pause, without rest, without slowing. And that number, vast beyond any ordinary reckoning, is the unit astronomers use to describe the nearest things. The star closest to our Sun, Proxima Centauri, sits 4.25 light years away. At the speed of the fastest spacecraft humanity has ever launched, New Horizons, which left Earth in 2006 and crossed the orbit of Neptune in just over 3 years. It would take approximately 80,000 years to reach Proxima Centauri. Not 80,000 days, not 80,000 months, 80,000 years, more than 3 times longer than all of recorded human civilization. And Proxima Centauri is our nearest neighbor. It is, in the context of the galaxy, essentially adjacent. The star cluster we call the Pleiades, that faint smear visible on clear winter nights that has been named and storied by cultures from ancient Greece to the Aboriginal peoples of Australia to the Aztec civilization, lies 440 light years away. The center of our own galaxy, the Milky Way, is 26,000 light years from Earth. The nearest large galaxy to our own, the Andromeda galaxy, the most distant object the naked human eye can see, hangs 2.5 million light years away in the darkness. On a clear autumn night in the northern hemisphere, you can find it as a faint smudge near the constellation Cassiopeia. The light entering your eye right now left Andromeda before Homo sapiens existed as a species, before the first stone tools were nabbed, before the last common ancestor of humans and Neanderthals had drawn breath. That light has been traveling through empty space for 2.5 million years to reach the lens of your eye tonight. These distances are not metaphors. They are not poetic exaggerations meant to inspire awe. They are measurements made with instruments of extraordinary precision, confirmed by independent methods, checked and rechecked across more than a century of observation. And yet, the strange truth of modern cosmology is that all of these distances, Proxima Centauri, the Pleiades, the galactic center, even Andromeda, are local. They are nearby, they are in the language of the universe, practically next door, because beyond all of that lies the true structure of space. A structure so immense that the galaxy we call home, the Milky Way with its 400 billion stars, is not even a rounding error. A structure built over billions of years by forces that operated silently, invisibly, at scales that dwarf every human concept of size. Understanding that structure, how it formed, what it means, and what it implies about the cosmos we inhabit is one of the central projects of modern science. It is a project that has already produced results more astonishing than anything the human imagination had previously dared to propose. To understand the large-scale structure of the universe, you must first abandon the image of space as a kind of featureless emptiness, a dark ocean in which galaxies float like isolated islands. That image was never accurate, but for most of human history it served well enough because we lacked the tools to see anything different. The shift came gradually, then all at once. In the late 19th century, astronomers began to notice that the fuzzy objects they called nebulae, the ones that clearly were not stars, were not distributed randomly across the sky. They clustered, they congregated. In the constellation Virgo alone, there appeared to be an unusual concentration of these objects, a gathering that hinted at something organized beneath the apparent chaos of the night sky. It took decades to understand what that organization meant. The nebulae, it turned out, were not clouds of gas within the Milky Way, but independent galaxies, each containing hundreds of billions of stars, each separated from our own by distances measured in millions of light years. This realization, achieved definitively by Edwin Hubble in the 1920s, was one of the most dramatic expansions of the known universe in all of history. Overnight, the cosmos grew from a single galaxy to a universe containing billions of them. And once that was established, a new question immediately arose. How were these galaxies arranged in space? The answer came from a technique called redshift measurement. When a galaxy moves away from us, the light it emits is stretched by the expansion of space between us and it. The wavelengths of that light become longer, shifted toward the red end of the spectrum. By measuring how much a galaxy's light has been redshifted, astronomers can calculate how far away it is. Hubble himself noticed in 1929 that galaxies appear to be receding from us at speeds proportional to their distance, a relationship now known as Hubble's law, which was the first direct evidence that the universe is expanding. This expansion does not mean that everything is flying away from a central point in space. It means that space itself is growing. Every sufficiently distant galaxy is receding from every other galaxy. Not because the galaxies are moving through space, but because the space between them is increasing. There is no center to this expansion, and no edge. The universe expands from everywhere simultaneously, beginning in the 1970s and accelerating through the 1980s and 1990s. Large surveys mapped the positions of thousands, then tens of thousands, then hundreds of thousands of galaxies in three-dimensional space. The CFA Redshift Survey, the Las Campanas Redshift Survey, and eventually the Sloan Digital Sky Survey collected spectra, and therefore distances, for galaxies across enormous swaths of the sky. What those maps revealed was not what anyone had expected. Galaxies are not distributed uniformly. They are not even approximately uniform. They cluster into groups, and groups cluster into clusters, and clusters assemble into superclusters. And the superclusters themselves are not isolated masses scattered evenly through space. They form an intricate, interconnected network, a cosmic web of immense sheets and filaments of matter, surrounding vast regions of nearly empty space. The structure that emerged from those surveys looked, to some researchers, like a foam of soap bubbles. To others, it resembled a sponge. To others, still, it looked like the neural network of some unimaginably large brain. Whatever the metaphor, the reality was consistent. Matter in the universe is organized in a pattern of breathtaking complexity, and that pattern extends in every direction as far as we can observe. Our own position within this structure is now fairly well mapped. The Milky Way belongs to the local group, a gravitationally bound collection of more than 50 galaxies dominated by two large spirals, the Milky Way and Andromeda, with the third largest member, the Triangulum galaxy, contributing a modest fraction of the group's total mass. The local group occupies a volume of space roughly 10 million light-years across. Beyond the local group, the next significant gravitational influence is the Virgo cluster, a dense concentration of more than 1,300 galaxies located approximately 54 million light-years away, containing several massive elliptical galaxies including M87, famous for hosting one of the largest supermassive black holes ever directly imaged. The Virgo cluster is the heart of a larger structure called the Virgo supercluster, also known as the local supercluster, which itself contains dozens of galaxy groups and clusters arranged in a flattened, irregular distribution several 100 million light-years across. For decades, the local supercluster was thought to represent the highest level of gravitational organization. Then, in 2014, a team of astronomers led by Toney published a new analysis of galaxy peculiar velocities, the component of galaxy motion attributable to local gravity rather than general cosmic expansion, and identified a far larger structure of which the Virgo supercluster is just one lobe, the Laniakea supercluster. Laniakea, whose name comes from a Hawaiian phrase meaning immeasurable heaven, contains the mass of approximately 100 million billion suns, encompasses roughly 500 million light-years in its longest dimension, and includes about 100,000 galaxies. The Milky Way sits near the outer edge of Laniakea, in a relatively sparse suburb of what is, by any measure, an enormously complex gravitational landscape. The filaments of this cosmic web are structures made primarily of dark matter, that invisible non-luminous substance which neither emits nor absorbs light, but which outweighs ordinary visible matter by a factor of roughly 5-1. Dark matter does not interact with light. It cannot be detected by any telescope, regardless of which wavelength the telescope is designed to observe. Its existence is inferred entirely from its gravitational effects, the way it causes galaxies to rotate faster than the visible matter alone could explain, the way it bends light from background sources through gravitational lensing, and the way it provides the scaffolding on which the cosmic web is built. Without dark matter, the universe we observe would be impossible to explain. In the early universe, ordinary matter was coupled to radiation. The two were locked together in a hot plasma that prevented ordinary matter from clumping under its own gravity. The density fluctuations in that plasma were too small and the time available too short to produce the galaxies and clusters we see today. Dark matter, however, was decoupled from radiation from the very beginning. It began clumping immediately after the Big Bang, building up gravitational wells, halos of dark matter that eventually grew large enough to capture ordinary matter as the universe cooled. The galaxies we see today formed inside these pre-existing dark matter hollows, like water pooling in the hollows of a landscape shaped by forces that preceded and outlasted the water itself. Along the skeleton of dark matter filaments, ordinary gas accumulates, cools, and eventually condenses into stars and galaxies. The galaxies themselves trace the underlying dark matter structure the way lights on a wire trace the wire. They reveal the shape of something larger that cannot itself be directly seen. Where filaments intersect, matter concentrates into clusters and superclusters. Between the filaments where the threads of the web grow thin and finally vanish lie the voids. The Coma cluster, located about 320 million light-years away in the direction of the constellation Coma Berenices, is one of the largest and best-studied galaxy clusters known. It contains over 1,000 catalogued galaxies within a region roughly 20 million light-years across, most of them elliptical and lenticular galaxies rather than the spiral types common in less dense environments. The total mass of the Coma cluster, including dark matter, hot gas, and the galaxies themselves, is approximately 10,000 times the mass of the Milky Way. It was observations of the Coma cluster in the 1930s that first led the astronomer Fritz Zwicky to conclude that the visible matter in the cluster was insufficient to hold it gravitationally together. There had to be additional invisible mass. Zwicky called it dunkel Materie, dark matter. His conclusion was met with skepticism at the time, but decades of subsequent observation have confirmed that he was right, and that dark matter is not a local peculiarity of the Coma cluster, but a universal feature of the cosmos. The Perseus cluster, located about 240 million light-years away, is another extraordinary concentration of galaxies,
and one of the brightest X-ray sources in the sky. Galaxy clusters are not empty between the galaxies.
They are filled with a hot, diffuse gas, the intracluster medium heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster. This gas emits X-rays, and by studying those X-rays, astronomers can measure the temperature, density, and chemical composition of the gas, as well as track the effects of the supermassive black holes at the centers of the brightest cluster galaxies on the surrounding medium. Voids are perhaps the strangest and least discussed features of the cosmic web. They are not absolute emptiness. A true vacuum, perfect and featureless, does not appear to exist anywhere in the observable universe, but they are regions of space so depleted of ordinary matter, so sparsely populated by galaxies, that they function almost as the negative image of the structure around them. Where filaments and walls concentrate matter, voids dilute it. Where clusters teem with hundreds or thousands of galaxies in a small region of space. A void might contain fewer galaxies than you could count on your fingers, spread across a volume hundreds of millions of light years across. The largest voids known, sometimes called supervoids, are among the most extreme environments in the observable universe. In a void, where matter is sparse and gravitational attraction is weak, the expansion of the universe proceeds faster than in denser regions. A void is a region where the universe is, in some measurable sense, less like itself. To travel toward one of these great voids, you would not simply pass through featureless space. Space is never featureless, even in the relatively empty local neighborhood of the Milky Way. There are structures to navigate, objects to observe, phenomena to register. Consider the approach to the local void. A genuine supervoid that begins almost on our cosmic doorstep, at the outskirts of the Virgo supercluster, and extends outward for roughly 230 million light-years in the direction of the constellation Aquila. The local void is one of the reasons the Milky Way is moving in the direction it is. The relative emptiness behind us creates a subtle gradient in the gravitational field, and our galaxy, along with all the others in the local group, is being gently pushed away from that emptiness and pulled toward denser regions elsewhere. This push from the void turns out to contribute roughly as much to the Milky Way's peculiar velocity as the pull from the dense concentrations of matter in the opposite direction. In the direction of the local void, the sky is dominated by the constellations Aquila the Eagle, Serpens the Serpent, and Ophiuchus the Serpent Bearer. These are among the oldest defined constellations in human history. Ophiuchus appears in Babylonian astronomical records. Its stars were important to navigators and calendar keepers across the ancient world. The brightest star in Ophiuchus, Rasselhage, is an A-type giant approximately 47 light-years from Earth, spinning so rapidly that its equatorial diameter is noticeably larger than its polar diameter. It is detectably oblate, a fact revealed by precise interferometric measurements in the early 21st century. Moving outward through Ophiuchus at the speed of light would take you past Rasselhage in 47 years. Then past the unremarkable field stars that crowd that region of sky, and eventually out of the disk of the Milky Way entirely, into the halo where old globular clusters orbit far above the galactic plane, and then into the intergalactic space where the local group thins and the local void begins. A hypothetical observer placed somewhere deep within the local void would find themselves in a profound isolation. Their sky would still contain galaxies. Voids are not absolute empty, but those galaxies would be distant, separated by unusually large gaps. The nearest galaxy clusters would be hundreds of millions of light-years away. The cosmic web that structures the rest of the universe would be visible only as a distant pattern, something happening elsewhere at the edge of perception. The night sky from within a supervoid would be darker than the night sky from Earth, in a way that goes beyond the absence of city lights or atmosphere. The nearest bright galaxies would be fainter and farther separated. The Milky Way if you happen to be inside a void, but in a position analogous to our own within a spiral galaxy, would look the same from the inside. But the extragalactic universe around you would look emptier, the voids larger, the filaments thinner. Voids also contain something unexpected, a subtle excess of dark energy's influence, because voids are underdense in matter. The repulsive effect of dark energy, the mysterious component that causes the expansion of the universe to accelerate, is less opposed by gravity inside the void than it is in denser regions. The rate of cosmic expansion inside a large void is measurably faster than the cosmic average. This has an observational consequence. Photons of light passing through a large void lose a small amount of energy, because they fall into the void's shallow gravitational well as they enter and lose more energy climbing out the other side than they gained going in, thanks to the accelerating expansion that has deepened the void while the photons were crossing it. This effect, called the integrated Sachs-Wolf effect, imprints a faint cold signature on the cosmic microwave background, in the direction of large voids, something we will return to when we discuss the most anomalous cold region in the entire observable sky. The question of isolation brings us to something that human beings find deeply strange and difficult to hold in the mind simultaneously with all the rest of what we know about the cosmos. The universe is not static, it is expanding. And that expansion means that the universe as we experience it, the observable universe, the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, is not the same as the universe as it exists. Some of what we see in the night sky is history. The light from Andromeda that enters our telescopes tonight left that galaxy 2.5 million years ago. The most distant galaxies we can detect sent their light toward us 10 or 12 billion years ago, when the universe was young and the galaxies within it were young as well. This creates a curious and unsettling asymmetry in our knowledge. We know the universe in two senses simultaneously, in space, as it is arranged right now, and in time, as it existed at progressively earlier epochs the farther we look. When we observe a galaxy 10 billion light years away, we are seeing it as it was when the universe was only about 4 billion years old. The galaxy that exists at that location today, if it still exists, if it has not merged with neighbors or been disrupted by some catastrophe, is not the galaxy we see. We are looking at a fossil of something that has since grown and changed and perhaps become entirely different in character. It is as though you're reading a letter that describes events 10 years in the past, from a person who may or may not still be alive, living in a city that may or may not still stand. This temporal depth connects naturally to a question that seems at first almost too simple to take seriously. How old are you? Not on Earth, where the answer is fixed by biology and birth records and the calendar, but in the cosmos more generally, where the very units of time are not universal but depend on where you happen to be and how that location is moving through space. This is not a philosophical puzzle but a physical one. Time, as Einstein demonstrated, is not absolute. It flows at different rates depending on velocity and gravitational field. A clock moving through space runs slower than a stationary clock. A clock in a strong gravitational field runs slower than one in a weak field. These effects are not theoretical curiosities, they are measured. They are incorporated into the software of GPS satellites, because without correcting for them, the satellite's position calculations would drift by kilometers per day. The GPS system you use to navigate a city depends on calculations that account for both special relativistic time dilation. The satellites are moving fast relative to the ground and general relativistic time dilation. The satellites are in a weaker gravitational field than the ground. Both effects are real. Both are measured. Both matter.
Each planet in our solar system moves at a different velocity through space and experiences a different gravitational field from the Sun.
Jupiter, massive and relatively far from the Sun, moves at about 13 kilometers per second in its orbit. Mercury, small and close to the Sun, moves at nearly 48 kilometers per second. Earth moves at about 30 kilometers per second. These differences in velocity and gravitational environment mean that clocks in different parts of the solar system run at subtly different rates relative to each other. If you were born on Mercury, not literally, but as a thought experiment, your year would be 88 Earth days long. An 18-year-old in Mercury years would be, by Earth reckoning, just over 4 Earth years old. The opposite kind of stretching happens with the slow outer planets. Neptune takes 165 Earth years to complete a single orbit. An 18-year-old in Neptune years would be nearly 3,000 Earth years old, born in other words. In approximately the time of ancient Rome, Saturn requires 29.5 Earth years per orbit. Jupiter needs nearly 12. Uranus takes 84 Earth years. An 18-year-old on Uranus would be roughly 1,500 Earth years old. 1 Uranian year spans the entire medieval period of European history. Venus offers a particularly strange case. Venus takes 224 Earth days to complete one orbit around the Sun. But Venus rotates so slowly on its own axis and in the retrograde direction opposite to most planets that a Venusian solar day, the time from one sunrise to the next on the Venusian surface, is actually longer than a Venusian year. A single day on Venus, in other words, is longer than the entire Venusian year. For a hypothetical inhabitant of Venus, the concept of a day and the concept of the concept of a year would be inverted from any intuition we carry from Earth. The sun would rise in the west, move slowly across the sky over the course of months, and set in the east, completing this cycle just over once for every Venusian orbit of the sun. These are not trivial variations. They change the fundamental texture of what time means in a given place. They point towards something deeper. The units of time that feel natural and absolute to us, the day, the year, the century, are products of our specific location and the specific orbital mechanics of our planet. They are as local and contingent as any other feature of our environment. The second itself, the fundamental unit of time in the International System of Units, is defined today in terms of atomic transitions in cesium, which is an improvement over the earlier astronomical definition, but still reflects a particular choice made by creatures who evolved on a particular planet. A civilization elsewhere in the galaxy, orbiting a different star at a different distance and rotating at a different rate, would arrive at entirely different natural units of time, and would find ours as arbitrary as we find the Venusian solar day. The question of what is universal in the cosmos, what holds equally everywhere, regardless of location, is one of the deepest in all of science. And it connects directly to one of the oldest and most persistent puzzles in cosmology. What is the shape of the universe itself? For most of human history, this question was not asked, because it seemed self-evident. Space was space. It extended in all directions, uniform and featureless and infinite. Newton's universe was Euclidean, flat in the geometric sense, meaning that parallel lines never converge or diverge, that the angles of any triangle sum to exactly 180 degrees, that the distance between 2 points is given by the simplest form of Pythagoras' theorem. This intuition matched everyday experience so well and was so useful for calculation that it was treated as obviously correct. Einstein changed everything. His general theory of relativity, published in 1915, demonstrated that space is not a fixed, neutral stage on which physical events take place. Space and time are a unified entity, space-time, and that entity can be curved by the presence of mass and energy. The Earth curves space-time.
the sun curves it more. A black hole curves it to an extreme that classical geometry cannot describe.
And the universe as a whole, filled with all the matter and energy it contains, has a curvature that is determined by its total content. The mathematics of general relativity admits three basic possibilities for the global geometry of space. If the universe contains enough matter and energy to reach or exceed a critical density, space curves back on itself, closing like the surface of a sphere. In such a universe, there is no center and no edge. A ray of light traveling in any direction would eventually return to its starting point. The way a traveler circumnavigating the Earth returns to the place they started without ever encountering a wall or a boundary. This is called positive curvature, and a universe with positive curvature is said to be closed. If the universe's density falls below the critical value, space is hyperbolic. It curves in the opposite sense, like the surface of a saddle. In a hyperbolic universe, parallel lines diverge. Triangles have angles that sum to less than 180 degrees. Such a universe is infinite with no boundaries, but its geometry is profoundly different from the flat Euclidean space of Newton. And if the universe happens to contain exactly the critical density, not a gram more, not a gram less, space is flat. Not flat in the sense of two-dimensional, but flat in the sense of Euclidean. Parallel lines remain parallel. Triangles have angles summing to exactly 180 degrees, and the universe extends infinitely in all directions without curvature. This is the case that Einstein's equations leave balanced on a knife edge, and it is remarkably the case that observational evidence most strongly supports. There is a fourth possibility that the simple classification of curved versus flat does not capture topology. Two spaces can have the same curvature, can be, in the sense of their local geometry, identical, while having completely different global topology. A flat infinite plane and the surface of a torus, the shape of a donut, are both locally flat. In both, the angles of a triangle sum to 180 degrees, and parallel lines remain parallel, but the torus is finite. If you travel in a straight line in one direction, you eventually return to where you started. The universe might be topologically non-trivial in this sense. It might be finite without being closed in the sense of positive curvature. Searches for signatures of a finite topology, patterns of repeated galaxy positions, or matching patches on opposite sides of the microwave background sky have so far found nothing convincing. But the search is ongoing, and the universe is under no obligation to make itself obvious. The tool that has allowed cosmologists to probe the curvature of the universe with high precision is the cosmic microwave background radiation. This is light, not visible light, but microwave radiation that was emitted when the universe was approximately 380,000 years old. Before that moment, the universe was too hot and too dense for light to travel freely. Photons were constantly scattered by the dense plasma of electrons and protons that filled all of space. Then, as the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. And suddenly the universe became transparent. The photons that had been trapped were released, and they have been traveling freely through space ever since, gradually losing energy as the universe expanded around them. Today, that ancient light fills the entire observable universe at a temperature of approximately 2.7 degrees above absolute zero. It arrives at our detectors from every direction in the sky, with almost exactly the same temperature everywhere. The deviation from perfect uniformity is only about 1 part in 100,000. But that tiny deviation matters enormously, because it encodes information about the physical conditions of the very early universe and about the geometry of the space through which the light has traveled since. The pattern of temperature variations in the cosmic microwave background has a characteristic angular scale, the typical size of the hot and cold patches on the sky. That scale depends sensitively on the curvature of the universe. Measurements made by satellites including COBE, WMAP and Planck, dedicated to mapping the microwave background with increasing precision, have found that the patches appear at almost exactly the size predicted for a flat universe. The conclusion, subject to small residual uncertainties, is that the universe is flat to within about half of 1%. But flat and infinite raises its own puzzles. An infinite universe contains an infinite amount of matter and energy, an infinite number of galaxies, an infinite number of stars, an infinite number of planets, and by straightforward combinatorial reasoning, an infinite number of places with conditions similar to those on Earth. In an infinite universe, not only is anything possible, everything that is possible happens an infinite number of times. The logic is impeccable, the implications are staggering. Before even the Big Bang created the conditions for that vertigo, before there was space or time in any meaningful sense, before the first particles of matter came into existence, there was, according to our best current understanding, a state that defies ordinary description. Not darkness, not emptiness, not a void before the Big Bang. There was no space. There was no time. There was not even nothing in the ordinary sense of that word, because nothing implies a container, a space in which nothing exists. What preceded the Big Bang, if preceded even means anything in the absence of time, remains one of the deepest unresolved questions in all of physics. What we can say is that the observable universe began from a state of extraordinary density and temperature. In the first fractions of a second, the universe was so hot that the known forces of nature were unified, indistinguishable from each other. As it expanded and cooled, those forces separated, acquiring the different properties they have today. The process by which this happened was not smooth and gradual. The very early universe underwent at least one phase transition, a sudden change in the state of its fields, analogous to the way water suddenly freezes when cooled through 0 degrees Celsius, releasing latent heat and changing its properties discontinuously. The phase transition that separated the strong nuclear force from the electroweak force is believed to have triggered a period of extraordinarily rapid expansion called inflation. Inflation is one of the most powerful and most debated ideas in modern cosmology. The proposal, developed by Alan Guth and others beginning in the early 1980s, holds that in the first tiny fraction of a second after the Big Bang, something like 10 to the power of negative 36 seconds, the universe expanded exponentially, doubling its size every 10 to the power of negative 37 seconds or so, for a period lasting perhaps 100 of those doublings. In that brief interval, a region of space smaller than a proton expanded to a size larger than an orange. The observable universe today, which we think of as vast, was entirely contained within that orange-sized region. Inflation was proposed to solve several problems with the standard Big Bang model. One is the horizon problem. The cosmic microwave background has the same temperature to 1 part in 100,000 everywhere in the sky, including regions that appear to be too far apart to have ever been in contact with each other. How did they come to the same temperature? Inflation answers this by pointing out that before inflation, these regions were extremely close together and did have time to thermalize. Inflation then stretched that uniform thermalized patch to enormous size. A second problem inflation solves is the flatness problem. For the universe to be as flat as we observe it today, its density at early times must have been tuned to the critical value with extraordinary precision, a precision so extreme that it seems to require explanation. Inflation naturally drives the geometry toward flatness. Because exponential expansion irons out any initial curvature, the way rapidly inflating a balloon irons out the wrinkles in its surface. And inflation makes a prediction. It predicts that the density fluctuations in the early universe, the seeds of all subsequent structure, should have a specific statistical character,
arising from quantum fluctuations in the inflaton field that were stretched to macroscopic scales by the rapid expansion.
Those fluctuations should follow a nearly scale-invariant power spectrum, fluctuations of roughly equal amplitude on all scales. When the cosmic microwave background was mapped by WMAP and Planck with sufficient precision to test this prediction, the result was a striking confirmation. The fluctuations are nearly scale invariant, with a small tilt in exactly the direction predicted by the simplest inflationary models. This agreement between theory and observation is one of the strongest pieces of evidence we have that inflation, or something very much like it, actually happened. In the first 3 minutes after the Big Bang, as inflation ended and the universe continued to cool through more ordinary expansion, conditions allowed protons and neutrons to fuse together into the nuclei of light elements, hydrogen, helium, and tiny traces of lithium and beryllium. This process, called Big Bang nucleosynthesis, established the basic chemical composition of the universe, roughly 3/4 hydrogen by mass and 1/4 helium, with everything else in quantities so small as to be almost negligible. The abundances of helium and deuterium, a heavy isotope of hydrogen predicted by nucleosynthesis theory, depend sensitively on the density of ordinary matter in the early universe, and the observed abundances match the predictions with impressive precision. This concordance is one of the 3 classic pillars of Big Bang cosmology, along with Hubble expansion and the cosmic microwave background. It is from this starting composition that all subsequent chemistry has derived. The carbon in your body, the oxygen in the air, the iron in your blood. None of these elements existed at the moment of the Big Bang. They were forged later in the nuclear furnaces of stars. In the core of a star like the Sun, hydrogen fuses to helium over billions of years, releasing the energy that lights the star. When a star like the Sun exhausts its hydrogen, it expands into a red giant, then fuses helium into carbon and oxygen, then expels much of its outer layers as a planetary nebula and collapses its core into a white dwarf, a dense, slowly cooling ember about the size of Earth. More massive stars proceed further. Carbon fuses to neon, neon to oxygen, oxygen to silicon, silicon to iron. At iron, the process stops. Iron has the most stable nucleus of any element. Fusing it absorbs energy rather than releasing it. When the iron core of a massive star reaches the mass of about 1.5 times the Sun, it collapses catastrophically in less than a second, triggering a supernova explosion that briefly outshines the entire galaxy containing it. In that explosion, and in the aftermath, elements heavier than iron are produced: gold, silver, platinum, uranium, and scattered into the interstellar medium. The heaviest elements are largely produced in neutron star mergers, collisions between the ultra-dense remnants left behind by supernovae. You are made of stardust in the most literal possible sense. The calcium in your bones was produced in a supernova that exploded billions of years before the Sun formed. The gold in any jewelry you might be wearing was likely created in a neutron star merger even earlier. The iron in your blood, the oxygen in your lungs, the carbon in every molecule of every cell, all of it was synthesized inside stars that died before our solar system existed and scattered into the interstellar medium and eventually incorporated into the molecular cloud that collapsed to form the Sun and the planets. We are the universe thinking about itself. As one astronomer put it, that is not poetry, it is chemistry and nuclear physics. Stars begin not in the dramatic fires of nuclear fusion, but in the cold, patient accumulation of dust and gas. The raw material of stellar birth is the interstellar medium, the thin, diffuse material that fills the space between stars within a galaxy. This medium is not uniform. It is structured into clouds, and within those clouds there are regions of especially high density, where temperatures are so low, sometimes as cold as minus 260 degrees Celsius, just 13 degrees above absolute zero, that complex molecules can form and survive. Molecules of water, ice, ammonia, methanol, formaldehyde, even glycine, the simplest amino acid, have been detected in interstellar molecular clouds. The chemistry of the universe is not confined to the surfaces of planets. It occurs everywhere that temperatures are low enough and densities high enough for molecules to form and survive. Within molecular clouds, certain compact regions called Bock globules stand apart as some of the most extreme environments in the interstellar medium. Named for the astronomer Bart Bock, who first proposed in 1947 that they might be the sites of stellar birth. These structures appear on astronomical photographs as dark, opaque patches silhouetted against the glowing gas behind them. They are small by cosmic standards, typically between 1 and 50 light years across. But within that volume, they contain enough mass to form one or several stars. Within a Bock globule, a cubic centimeter of space may contain thousands of molecules, compared to the near total emptiness of the surrounding interstellar medium. Inside these dense cold cocoons, gravity is slowly winning a battle against the thermal pressure that would otherwise disperse the gas. As a globule contracts, its core density increases. The material in the center begins to fall inward, slowly at first, then faster. As infalling gas compresses, it heats. The temperature at the core rises from a few degrees above absolute zero to thousands of degrees, then tens of thousands. The opacity of the surrounding material traps this heat, so the protostar, for that is what the collapsing core has become, glows invisibly in the infrared while remaining completely hidden from optical telescopes by the dust of the globule itself. This invisible phase of stellar birth lasts hundreds of thousands of years. Eventually, the temperature and pressure at the center of the collapsing core reach the threshold for nuclear fusion. Approximately 10 million degrees Celsius for the fusion of hydrogen into helium. When that threshold is crossed, a new energy source ignites at the core. The outward pressure of radiation from nuclear fusion eventually balances the inward pull of gravity, and the collapse stops. A star has been born. The sculpted structures at the edges of star-forming regions, towers and pillars of gas and dust carved by the radiation from newly born massive stars, are among the most visually striking objects in the cosmos. The pillars of creation, photographed by the Hubble Space Telescope in 1995, in a region of the Eagle Nebula, about 6,500 light-years away, are perhaps the most famous example. Columns of molecular hydrogen and dust several light-years tall, slowly being eroded by ultraviolet light from hot young stars nearby. Within those pillars, new stars are forming even as the pillars themselves are being destroyed. The pillars are expected to vanish entirely within roughly 100,000 years, destroyed by the radiation from the very stars their material helped to create. Among the most dramatic regions of active star formation in the Milky Way is the Carina Nebula, located about 7,500 light-years away. The Carina Nebula is home to some of the most massive and luminous stars known, including Eta Carinae, a binary system estimated to have 60 to 100 times the mass of the Sun and producing 5 million times its luminosity. Eta Carinae is so bright and so massive that it is profoundly unstable. It underwent a catastrophic eruption in the 1840s that briefly made it the second brightest star in the night sky. It is expected on astronomical timescales to end its life as a supernova or even a hypernova. The Tarantula Nebula, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 160,000 light-years away, is the most luminous star-forming region in the local group. It contains the star cluster R136, whose most massive known member, R136A1, has a mass approximately 215 times the mass of the Sun and is about 8 million times more luminous. If R136A1 were placed at the center of our solar system, its radiation would strip Earth's atmosphere in a geologically brief time. At its distance in the Magellanic Cloud, it contributes significantly to the illumination of its entire surrounding nebula. Stars of this mass exist at the edge of stability. Radiation pressure from their cores is barely contained by gravity, and they lose mass continuously through powerful stellar winds. But even among all the extraordinary structures and phenomena of the observable universe, there are anomalies, things that do not fit neatly into the framework of our best theories, things that point toward gaps in our understanding, things that force cosmologists to consider possibilities they would rather not have to consider. One of the most puzzling such anomalies is a feature of the cosmic microwave background, a region of unusual coldness in the direction of the constellation Eridanus, known as the cold spot. The cosmic microwave background, as we have noted, is almost perfectly uniform. The temperature variations that do exist are tiny, amounting to fluctuations of only tens of millionths of a degree from the average. These fluctuations are understood within the standard cosmological model as the imprint of quantum fluctuations in the very early universe, inflated to cosmic scales by inflation, and then frozen into the pattern of density variations from which all subsequent structure grew. Given that framework, the statistical properties of the temperature pattern in the microwave background can be calculated precisely. The cold spot, located in the direction of the constellation Eridanus, roughly 3 billion light-years from Earth, is a region of the microwave background approximately 5 degrees across in the sky and roughly 70 microkelvins colder than the average temperature of the background. The average deviation of background temperature fluctuations is only about 18 microkelvins. The cold spot is dramatically anomalously cold relative to its surroundings. Since its discovery by the WMAP satellite in 2004, the cold spot has attracted enormous attention and generated an extraordinary variety of proposed explanations. One proposal invoked the integrated Sachs-Wolf effect. As microwave background photons pass through a large cosmic void, they gain energy entering the void's gravitational well and lose energy leaving it. If the universe is accelerating in its expansion, photons lose more energy leaving the void than they gain entering it, resulting in a cold patch in the sky in the direction of the void. A survey of galaxies in the direction of the cold spot did reveal an unusual absence of galaxies, a supervoid, lending some support to this explanation. But calculations suggest that the void in question would need to be roughly 2 billion light-years across and anomalously empty, more empty than standard cosmological models allow for a structure that size. A more exotic proposal holds that the cold spot might be evidence of a collision between our universe and another. In the framework of eternal inflation, the process that produced the Big Bang is not a unique event, but an ongoing one. The universe we inhabit is one bubble in a vast, possibly infinite multiverse of bubbles, each with its own physical laws, its own constants, its own history. Occasionally in this picture, two bubbles come close enough to interact. If our universe grazed another bubble universe in the distant past, the collision would have imprinted a distinctive signature on the cosmic microwave background. The cold spot is, at least superficially, consistent with this picture. The multiverse proposal is speculative. It makes predictions that are difficult or impossible to test with current or foreseeable instruments. But the cold spot's very existence, its refusal to yield to simpler explanations, has kept the more radical possibilities alive in the scientific literature. It is a reminder that the universe's willingness to surprise us has not diminished as our instruments have grown more powerful. The most extreme concentrations of matter in the universe are not galaxy clusters. They are black holes. A black hole is a region of space in which the curvature of space-time produced by a concentrated mass has become so extreme that nothing, not matter, not light, not information of any kind, can escape from inside a certain boundary called the event horizon. Inside the event horizon, the geometry of space-time is so severely warped that all paths through space in every possible direction lead toward the central singularity. To fall through an event horizon is to enter a region where the future leads only inward. For a distant observer watching something fall toward the black hole, the experience of the infalling object would appear to slow dramatically as it approached the event horizon due to the extreme gravitational time dilation in that region. The infalling object would appear to redden and dim and freeze at the horizon and would fade from visibility, but it would never quite appear to cross the horizon. From the perspective of the infalling observer, however, no such hesitation occurs. The passage through the event horizon happens in a finite proper time and is for a sufficiently large black hole not accompanied by any unusual physical experience at the moment of crossing. But inside the horizon, things become stranger still. General relativity predicts that within a rotating black hole, and almost all astrophysical black holes are rotating, because they form from collapsing matter that carries angular momentum. There exists a second boundary interior to the event horizon. This inner boundary is called the Cauchy horizon. At and inside the Cauchy horizon, the structure of space-time undergoes a qualitative change. Deterministic predictability breaks down. An observer crossing the Cauchy horizon would, in principle, be exposed to information from the entire future history of the universe outside, compressed into a flash of infinitely blue-shifted radiation. Whether the Cauchy horizon can actually be crossed, or whether quantum effects destroy it before any physical observer can reach it, is one of the open questions in theoretical physics. The strong cosmic censorship conjecture proposed by Roger Penrose holds that the Cauchy horizon is always unstable, that any real black hole develops a singularity at the Cauchy horizon that prevents any observer from crossing it. The question remains unresolved. At the center of virtually every large galaxy lies a supermassive black hole. The supermassive black hole at the center of the Milky Way, Sagittarius A, has a mass of approximately 4 million solar masses. The first direct image of a black hole, obtained by the Event Horizon Telescope collaboration in 2019, showed the silhouette of a supermassive black hole with a mass of 6.5 billion solar masses at the center of M87. The bright ring of light surrounding the dark shadow in that image is not the event horizon itself, but the photon sphere, a region where gravity is so strong that light can orbit the black hole, and from which photons only narrowly escape to reach our telescopes. When material falls into a supermassive black hole, it forms a hot accretion disk. A small fraction of this material is redirected by magnetic fields and ejected in twin jets of plasma traveling at velocities approaching the speed of light. These relativistic jets can extend for millions of light years, depositing enormous amounts of energy into the surrounding intergalactic medium. In the Perseus cluster, observations by the Chandra X-ray Observatory revealed that the jets from the central galaxy's nucleus are generating pressure waves, sound waves propagating through the hot intracluster gas at the lowest detectable frequency in the universe, approximately 57 octaves below middle C. Anomalies in the large-scale structure of the universe are not limited to the microwave background. The Sloan Great Wall, discovered in 2003, is a vast sheet of galaxies approximately 1 billion light-years long, located roughly 1 billion light-years from Earth. At the time of its discovery, it was the largest known structure in the universe. Standard cosmological theory predicts that the universe should appear homogeneous, statistically uniform on scales larger than approximately 300 million light-years. The Sloan Great Wall already violates this limit. The Hercules Corona Borealis Great Wall, if confirmed, extends over approximately 10 billion light-years, more than 30 times the predicted scale of homogeneity. These structures are not merely unexpected. They are, if confirmed, evidence that the standard cosmological model is missing something important. One place where our understanding of the large-scale dynamics of the universe is most dramatically tested is in the phenomenon of the Great Attractor. In the 1970s and 1980s, astronomers studying the peculiar velocities of galaxies noticed something strange. The Milky Way, along with the entire local group and the entire Virgo supercluster, was moving toward a specific point in the sky at a speed of hundreds of kilometers per second. Something with an enormous mass was pulling on us. The object responsible lay behind the zone of avoidance, a region of sky along the plane of the Milky Way where the dense concentration of gas, dust, and stars in our own galaxy makes it nearly impossible to observe distant objects in optical wavelengths. The tools of radio and X-ray astronomy, which can penetrate the dust of the galactic plane, were needed to look behind that curtain. What astronomers eventually found was not a single massive object, but an immense concentration of galaxies, the Shapley supercluster. Located approximately 650 million light-years from Earth, the Shapley supercluster contains the mass of 50 million billion solar masses. It is not simply massive. It is the gravitational anchor of a region of space so large that our own galaxy, our local group, our local supercluster, all of them together, are being tugged toward it at hundreds of kilometers per second. The Great Attractor itself, a massive concentration of galaxies in the Centaurus region about 250 million light-years away, accounts for roughly 40% of the peculiar motion of the local group. The Shapley supercluster drives much of the rest. And beyond the Shapley supercluster, the universe does not reveal its structure easily. And every answer leads to more questions about what lies beyond. There is another phenomenon that has transformed our ability to probe the large-scale structure of the universe in the last 3 decades. Gravitational waves predicted by Einstein's general theory of relativity in 1916. Gravitational waves are ripples in the fabric of spacetime produced by accelerating masses, specifically by asymmetric distributions of mass that change over time. For most of the 20th century, gravitational waves were theoretical constructs. Their existence was inferred indirectly from the behavior of binary pulsars, but they were never directly detected because the instruments required to measure them did not exist. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, changed that in September 2015. On the 14th of that month, both detectors of LIGO, one in Hanford, Washington, and one in Livingston, Louisiana, recorded a signal lasting roughly 0.2 of a second, a chirp rising rapidly in frequency and amplitude before falling away to nothing. Analysis of the signal revealed that it was produced by the merger of 2 black holes, each with a mass of about 30 solar masses, located approximately 1.3 billion light-years from Earth. In the final moments of the merger, the system radiated gravitational energy equivalent to 3 solar masses, more power than the combined luminosity of all the stars in the observable universe, in the form of gravitational waves. The peak amplitude of the space-time distortion reaching Earth was about 1,000th of the diameter of a proton. Since 2015, dozens of gravitational wave events have been detected, including mergers of binary black holes, binary neutron stars, and mixed systems. The binary neutron star merger detected in August 2017 was observed simultaneously in gravitational waves and in light, gamma rays, X-rays, ultraviolet, visible infrared, and radio by dozens of telescopes around the world and in space. This event confirmed that neutron-star mergers are a major site of heavy element production. The kilonova, the optical and infrared emission from the rapidly neutronized ejecta, carried away a mass of gold and platinum tens of times the mass of the Earth. Every gram of gold in the world ultimately has its origin in events like that one. Gravitational wave astronomy has opened a new window on the universe. It allows us to observe events black hole mergers in particular that are completely invisible in electromagnetic radiation because black holes by definition do not emit light. It probes physics at the most extreme densities and curvatures of space-time accessible to observation. And it provides an independent method of measuring the expansion rate of the universe, the Hubble constant, based on the gravitational wave signal of binary mergers, which encodes the distance to the source without requiring the calibration chains that affect other distance measurement methods. The gravitational wave measurement of the Hubble constant has the potential to resolve or to sharpen one of the most significant discrepancies in modern cosmology, the tension between the value of the Hubble constant measured from the local universe and the value inferred from the cosmic microwave background, a discrepancy that has grown in significance as both measurements have become more precise. There is a class of objects even denser than black holes, in the sense of being the densest stable matter in the observable universe, that gravitational wave astronomy has revealed in extraordinary detail: neutron stars. When a star with a mass between about 8 and 20 times the mass of the Sun exhausts its nuclear fuel, the iron core collapses in a fraction of a second, and the outer layers of the star are blasted away in a supernova. What remains of the core is a neutron star, a ball of matter perhaps 20 kilometers across, compressed to densities exceeding that of an atomic nucleus. At those densities, electrons and protons are forced together to form neutrons, and the star is supported against further collapse. Not by ordinary gas pressure or radiation pressure, but by neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which forbids two neutrons from occupying the same quantum state. A teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. A neutron star has a surface gravity approximately 200 billion times stronger than Earth's. At the surface of a neutron star, the escape velocity is roughly half the speed of light. If you could somehow stand on the surface of a neutron star, which you could not because your body would be compressed to a layer a few atoms thick by the tidal forces, the closest equivalent in human experience to what you might see is something no human has experienced. The star beneath you would be perfectly smooth to the touch, with surface irregularities no larger than a few millimeters. Any larger deviation would be crushed flat by gravity. The sky above you would appear to bulge inward, because the extreme curvature of space-time around the neutron star bends light significantly. Many neutron stars rotate rapidly and emit beams of radiation from their magnetic poles. When those beams sweep past the Earth with each rotation, like the beam of a lighthouse, we detect a precisely timed pulse of radio waves or X-rays. These objects are called pulsars, and some of them rotate hundreds of times per second, their timing so precise that they rival atomic clocks in stability. Millisecond pulsars, which rotate between a few hundred and nearly 1,000 times per second, are used as a galactic scale timing array. By monitoring the arrival times of pulses from many pulsars simultaneously, astronomers can detect correlated shifts that betray the presence of gravitational waves with wavelengths too long for ground-based detectors to measure, waves produced by pairs of supermassive black holes in the final stages of inspiral before merger, oscillating with periods of years to decades. It is against this backdrop of cosmic scale, cosmic violence, and cosmic time that the question of life acquires its full weight. We are not asking whether chemistry can produce self-replicating molecules. We know that it can. Because we are here, we are asking something more specific: whether the conditions that produced us are common or rare in the universe. Astrobiology has matured considerably in recent decades. driven partly by the discovery of extremophiles on Earth, organisms thriving in conditions long considered lethal, and partly by the revolution in exoplanet science. In the early 1990s, no planets outside the solar system had been confirmed. Today, more than 5,000 exoplanets are known, with thousands more candidates awaiting confirmation. The distribution of those planets reveals that planetary formation is common. The Milky Way contains, by current estimates, hundreds of billions of planets. The most promising candidate environments for life in our solar system beyond Earth include the subsurface ocean of Europa, a moon of Jupiter locked beneath an icy crust tens of kilometers thick, and the similar subsurface oceans believed to exist beneath the ice of Ganymede, Callisto, and Saturn's moon Enceladus. Enceladus is particularly interesting. Observations by the Cassini spacecraft detected geysers of water vapor and ice particles erupting from the south polar region, carrying with them organic molecules and molecular hydrogen, the latter indicating active hydrothermal chemistry on the seafloor of Enceladus's subsurface ocean. The ingredients for life by the standards of terrestrial chemistry are present. Whether life has taken advantage of them is unknown. Saturn's moon Titan presents a different and stranger case. Titan has a dense nitrogen atmosphere, the only moon in the solar system with a substantial atmosphere, and a surface where liquid methane and ethane replace water as the dominant surface liquid. Rivers of liquid methane carve channels in the ice. Lakes of liquid methane pool at the poles. It rains methane on Titan. Whether life could use liquid methane as a solvent, as life on Earth uses water, is a genuine scientific question, and one that cannot be answered without in situ investigation. The Dragonfly mission, a rotorcraft lander, is planned to explore the surface of Titan in the 2030s. The biochemistry of life as we know it, carbon-based, water-dependent, operating within a fairly narrow range of temperatures and pressures, may not be the only possible biochemistry. Life is the product of chemistry, and chemistry is extraordinarily versatile. Silicon, which shares chemical properties with carbon, can form long-chain molecules and might, under certain conditions, serve as the basis for a different kind of biochemistry. Ammonia, which is liquid at lower temperatures than water, has been proposed as a possible solvent for life in cold environments. But there is a deeper kind of strangeness to contemplate. We tend to think of life as something that requires a substrate, a body, a nervous system, a chemistry, a physical location. Yet the universe contains processes that are organized, that process information, that exhibit something that might be called behavior without any of those things. The dynamics of a galaxy, with its spiral density waves propagating through the disk over billions of years. The oscillations of a neutron star, spinning hundreds of times per second with a regularity that surpasses atomic clocks. None of these are alive, and yet none of them are simple, and the boundary between organized complexity and the simplest living systems is less sharp than it might seem among those billions of potentially habitable worlds. How many have developed life? We do not know. The sample size is one. We have exactly one data point on the development of life, the Earth, and from a single data point it is impossible to determine whether a phenomenon is universal, common, rare, or unique. The rapid appearance of life on Earth after the planet cooled sufficiently suggests to some that life appears quickly wherever conditions allow. The long delay between the origin of life and the emergence of complex multicellular organisms, about 3 billion years, and the apparent dependence of that emergence on a unique and perhaps improbable sequence of evolutionary events, suggests to others that complex life may be rare even where simple life exists. And the complete absence, so far, of any signal or artifact attributable to technological intelligence elsewhere in the galaxy suggests that either such intelligence is rare or that it does not survive long enough to be detectable, or that it is not communicating in ways we know how to listen for. The arithmetic of a large universe is generous with small probabilities. Rarity and solitude are not the same thing when the universe contains 2 trillion galaxies. Evolution does not have a preferred outcome. It produces organisms adapted to their environments. And environments in the universe differ from one another in ways that are almost incomprehensibly diverse. A world with gravity twice that of Earth would select for low, dense body plans. A world with a dense atmosphere and low stellar radiation might select for organisms that generate their own light through bioluminescence. A world of subsurface ocean with no solar input might produce life that has never experienced the sky, never had a concept of above and below in the sense we mean, never developed any sensory apparatus tuned to the wavelengths we consider visible light. And then there are the possibilities that reach beyond biology entirely. We do not know whether intelligence necessarily takes biological form. We do not know whether consciousness is substrate independent. These questions are not currently answerable by science, but the universe will not wait for us to answer them before producing whatever it is going to produce in the billions of years ahead. The observable universe is 13.8 billion years old. But the era of stars, the period during which nuclear fusion lights the cosmos, in which planets can form and life can arise, will last for trillions of years into the future. We are near the beginning of that era. As the universe continues to expand and cool, the formation of new stars will gradually slow. The most massive stars, which live for only millions of years, have already burned through most of their fuel and died. The Sun has another 5 billion years on the main sequence. The least massive red dwarf stars, which burn their hydrogen so slowly and so efficiently, will persist for 10 to 100 trillion years, thousands of times longer than the current age of the universe. Long after the Sun has become a white dwarf and the Earth has been consumed by its red giant phase, small red stars will still be illuminating their planets, still providing the energy gradients on which chemistry and perhaps life can run. After the last stars fade, the universe will enter a long dark period. White dwarfs will cool over trillions of years, eventually becoming invisible cold remnants called black dwarfs. Black holes will persist far longer, slowly evaporating through Hawking radiation, a quantum process by which pairs of particles are created near the event horizon, one falling in and one escaping on timescales so vast that they make the current age of the universe seem like a fleeting instant. A stellar mass black hole will take approximately 10 to the power of 67 years to evaporate. A supermassive black hole of 1 billion solar masses will take approximately 10 to the power of 96 years. By comparison, the current age of the universe is approximately 10 to the power of 10 years. After the last black hole evaporates, the universe will contain only a thin, cold soup of photons, neutrinos, and electrons and positrons, expanding forever into an ever colder emptiness. This is the future the standard cosmological model predicts if dark energy remains as it is today. There are alternatives. If dark energy grows stronger over time, a possibility called phantom energy. The repulsive force would eventually overcome all other forces, tearing apart first galaxy clusters, then galaxies, then solar systems, then planets, then atoms, in a sequence of events ending in what is called the Big Rip. If dark energy reverses and becomes attractive, an even more speculative possibility, the universe's expansion could halt and reverse, leading to a big crunch, a collapse of the entire observable universe into a final singularity. Which of these futures awaits us depends on the nature of dark energy, which remains one of the most profound mysteries in all of physics. Dark energy is the name given to whatever it is that causes the expansion of the universe to accelerate. It was discovered in 1998 by 2 independent teams led by Sol Perlmutter on one side and Brian Schmidt and Adam Rees on the other, who were measuring the distances and redshifts of type Ia supernovae in distant galaxies. Type Ia supernovae are believed to be standard candles. Their intrinsic luminosity is thought to be well determined by the physics of the explosion. So by measuring how bright they appear in the sky, astronomers can calculate how far away they are. The 1998 measurements found that distant supernovae were systematically fainter than expected, which meant they were farther away than expected, which meant the universe was expanding faster now than it was in the past. The expansion is accelerating. This was the opposite of what most cosmologists had expected. The conventional expectation was that the mutual gravitational attraction of all the matter in the universe would be gradually slowing the expansion, perhaps even eventually halting it and reversing it. Instead, the expansion is speeding up. Something is driving the acceleration. That something is called dark energy, and it comprises approximately 68% of the total energy content of the universe. Ordinary matter makes up about 5%. Dark matter makes up about 27%. Everything visible, every star, every galaxy, every planet, every atom of gas in every cloud, and every cluster is a small fraction of the total content of the universe. The universe is mostly made of things we do not understand. We look at the sky and we see a snapshot. Light that left its sources years and centuries and millions and billions of years ago, arriving at our eyes or our instruments in a single moment that we call the present. The universe that produced that light has already changed. The stars we see have aged, some have died, new ones have formed, galaxies that appeared well separated have drawn closer. The cosmic web has continued its slow evolution toward greater contrast, greater structure, denser filaments, and deeper voids. What we see is history, and yet we have always looked the human capacity to direct attention upward, outward, away from immediate survival and toward the horizon of the unknown, is itself one of the most remarkable features of the universe, a feature that appeared unpredicted by any prior physics in the late history of a small planet at the edge of an ordinary galaxy. Whether that capacity is unique in the universe, or whether it has arisen in other forms, in other places and other times, we cannot say. What we can say is that it exists here, that it has produced the knowledge contained in everything we have discussed, and that it shows no sign of having reached its limit. The universe will keep surprising us. The history of cosmology is a history of discoveries that shattered the assumptions of the previous generation. The discovery that the Milky Way is not the entire universe, that the universe is expanding, that expansion is accelerating, that most of the universe's mass is invisible, that the universe underwent an extraordinary inflationary expansion in its first moments. Each of these discoveries arrived at the edge of what previous technology could see and required new instruments and new mathematics to interpret. Each was resisted, then accepted, then incorporated into a new framework that in turn generated new predictions and new anomalies. We are living through another such period. The cold spot in the microwave background remains unexplained. The tension between different measurements of the Hubble constant has grown more acute as both measurements have become more precise, and no simple resolution has emerged. The nature of dark energy is entirely unknown. It may be the energy of empty space, as Einstein's cosmological constant suggests, or it may be a dynamical field that evolves over time, or it may be evidence that general relativity requires modification on cosmological scales. The origin of the magnetic fields that permeate galaxies, clusters, and the cosmic web, ordered fields on enormous scales whose origin no satisfactory theory has yet explained, is an open problem. The mechanism by which supermassive black holes grew so large so quickly in the early universe is unclear. The precise way in which dark matter halos assemble and merge, and how that process shaped the sizes and structures of the galaxies we observe, is still being refined. These are not failures. They are the normal condition of science at the frontier. Every question answered at sufficient depth reveals several more questions just behind it. The universe does not have a finite set of secrets that will eventually run out. It has, as far as anyone can determine, an inexhaustible depth. A willingness to reveal new structure and new puzzles at every scale, in every direction, in every domain of inquiry. The observable universe is enormous, but the universe itself, if it is infinite, as our best measurements suggest, is larger than any finite number can describe. Everything we have discussed, every object we have named, every structure we have mapped, every anomaly we have puzzled over, occupies a region of space that, if the universe is flat and infinite, is a set of measure zero within the whole. The galaxies we cannot see either because their light has not yet reached us, or because the universe's acceleration has carried them beyond the reach of any signal we could ever receive, vastly outnumber the galaxies within our observable horizon. The universe extends beyond what we can observe, and may extend beyond what we can even in principle ever observe. This is perhaps the deepest consequence of everything we have discussed. Not that the universe is large, though it is almost incomprehensibly large, but that it is young. Not in any ordinary human sense, 13 billion years dwarfs every human timescale. But in the sense that the processes now underway have barely begun. Stars will continue to ignite, planets will continue to form, chemistry will continue to organize itself into configurations of increasing complexity. And somewhere in the vast web of filaments, in the quiet neighborhoods of long-lived stars, in the cold, dense cores of molecular clouds where new stars are being born at this moment, the conditions for the next great surprise in the history of the cosmos are being assembled. We began with the number 9.5 trillion kilometers, the length of a single light year. We have since traveled in the imagination through the cosmic web to the edges of the observable universe, backward in time to the first moments after the Big Bang, inward to the dense cores of molecular clouds where stars are being born, and outward to anomalies in the oldest light in the universe that may be telling us something fundamental about the structure of reality. We have visited the extremes of matter in neutron stars and black holes, traced the origin of the atoms in our bodies to stellar explosions billions of years before the sun formed, and contemplated the long future of a universe that will outlast everything we know. And we have done all of this from the surface of a planet orbiting a star at a distance of 8 light minutes, using instruments built over the last few centuries, with mathematics developed over the last few thousand years. The universe is vast, it is old, its scale dwarfs everything we are and everything we have made, and yet it has in us produced entities capable of noticing that it is vast and old and of asking why. That is not a small thing. In a universe of empty space and cold gas and ancient light, the capacity for astonishment is rare enough that it may deserve attention. The questions that cosmology raises about the origin of structure, the nature of dark matter and dark energy, the geometry of space, the possibility of other universes, the conditions for life, are not merely scientific questions. They are questions about what kind of place the cosmos is and about what it means to exist within it. The answers continue to arrive, imperfect and incremental, each one opening new uncertainties. That process shows no sign of ending. The universe, it seems, is patient with our curiosity, and our curiosity in return has proven to be one of the few things equal to the scale of what we are trying to understand. There is a dimension of the cosmos that optical telescopes entirely miss, and that dimension contains some of the most powerful and revealing phenomena in the known universe. We see the sky in visible light wavelengths our eyes evolved to detect, because the sun, the star that powers life on this planet, emits most of its energy there. But the universe broadcasts on every frequency simultaneously, and most of those broadcasts are invisible to unaided human perception. Radio waves from the cosmos were first detected accidentally by Carl Jansky in 1932, when he was trying to identify sources of interference in transatlantic telephone communications and found that a steady hiss in his antenna was coming from the direction of the center of the Milky Way. The discovery launched radio astronomy, which has since become one of the most productive branches of observational science. With radio telescopes, astronomers can observe phenomena that are completely invisible to optical instruments. The cold hydrogen gas that traces the structure of the Milky Way, the jets of plasma extending from the nuclei of active galaxies, the precise pulses of millisecond pulsars, and the cosmic microwave background itself, the afterglow of the Big Bang. The 21 centimeter line of neutral hydrogen, a specific radio frequency emitted when the electron in a hydrogen atom flips its spin relative to the proton, is one of the most important tools in radio astronomy. Hydrogen is the most abundant element in the universe, and most of it exists in the cold, diffuse intergalactic and interstellar medium in neutral atomic form. By mapping the 21 centimeter emission across the sky and measuring the Doppler shifts of the emission from gas moving at different velocities relative to Earth, radio astronomers have mapped the spiral structure of the Milky Way, tracked the large-scale distribution of gas in other galaxies, detected hydrogen halos extending far beyond the visible boundaries of galaxies, and measured the rotation curves of galaxies, the observations that provided the most direct early evidence for dark matter. X-ray astronomy, which requires space-based instruments because Earth's atmosphere is opaque to X-rays, opened a view of the cosmos at temperatures of millions to billions of degrees. The objects that dominate the X-ray sky are extreme: neutron stars and black holes accreting material from companion stars, galaxy clusters filled with hot intracluster gas, active galactic nuclei blazing with the energy of matter falling into supermassive black holes. The Chandra X-ray Observatory, launched in 1999, has produced images of the X-ray universe with a resolution approaching that of the best optical telescopes, and the universe it reveals in that wavelength is one of constant violent energy exchange, of matter heated and compressed and accelerated to extreme states, of physical processes that operate at the boundary of what general relativity and quantum mechanics together can describe. Gamma-ray astronomy reaches to even higher energies. The Fermi Gamma-ray Space Telescope, launched in 2008, monitors the entire sky continuously for gamma-ray sources, including the brief but extraordinarily energetic bursts known as gamma-ray bursts. These events, the most energetic explosions in the observable universe since the Big Bang, release more energy in seconds to minutes than the Sun will emit in its entire 10 billion year lifetime. Some are produced by the collapse of massive rotating stars directly to black holes, the hypernova mechanism. Others arise from the merger of two neutron stars, or from the merger of a neutron star with a black hole. The gamma rays from these events travel across billions of light years, and the most distant gamma-ray burst detected so far was so far away that its light had been traveling for approximately 13 billion years when it arrived at our detectors, meaning the event occurred when the universe was less than 1 billion years old, and the star that produced it was among the first generation of massive stars to exist. Neutrino astronomy adds yet another messenger. Neutrinos are nearly massless, chargeless particles that interact with matter only through the weak nuclear force and gravity, which means they pass through almost everything. 1 trillion neutrinos from the Sun pass through every square centimeter of your body every second day and night, passing through the Earth as if it were not there. This same property makes neutrinos extraordinarily difficult to detect, but also uniquely valuable. They carry information from the interior of stars and from regions so dense that light cannot escape. In 1987, when the supernova SN 1987A exploded in the Large Magellanic Cloud, the closest supernova visible to the naked eye in nearly 4 centuries, neutrino detectors on Earth recorded a burst of neutrinos arriving approximately 3 hours before the light from the explosion arrived. Those neutrinos had escaped from the collapsing core of the star as the iron core imploded, while the light had to wait for the shock wave to reach the stellar surface. That 3-hour head start confirmed a fundamental prediction of core collapse supernova theory. The IceCube Neutrino Observatory at the South Pole, a cubic kilometer of Antarctic ice instrumented with thousands of photomultiplier tubes, has detected high-energy neutrinos from beyond the Milky Way, including a source that, when traced back through the sky, coincided with a blazar, a galaxy whose jet of relativistic plasma happens to point almost directly toward Earth. This result strongly suggests that active galactic nuclei are sources of some of the highest energy particles in the universe, and it demonstrates that multi-messenger astronomy, combining information from gravitational waves, electromagnetic radiation across all wavelengths, and now neutrinos, is providing a far richer picture of cosmic phenomena than any single messenger could. The extremely high-energy cosmic rays, protons, and heavier nuclei arriving at Earth with energies that dwarf anything achievable in human-built particle accelerators present one of the longest-standing mysteries in astrophysics. The Pierre Auger Observatory in Argentina, which covers an area larger than the state of Rhode Island and uses a combination of water, Cherenkov detectors, and fluorescence telescopes to detect the air showers produced when a cosmic ray hits the atmosphere, has detected particles with energies exceeding 10 to the power of 20 electron volts, about 40 million times the beam energy of the Large Hadron Collider. At these energies, protons are attenuated by interactions with the cosmic microwave background photons over distances of a few 100 million light-years. This means that the most energetic cosmic rays must originate relatively nearby in cosmic terms. The leading candidates for their sources are the jets of active galactic nuclei, but definitive identification of the sources of the most extreme cosmic rays remains elusive. There is a question that sits at the boundary of astrophysics and particle physics, and that connects directly to the dark matter problem. What physically is dark matter? The name is a description of ignorance, not understanding. We know dark matter exists. The evidence is overwhelming and convergent from dozens of independent lines of observation. We know approximately how much of it there is. We know that it clusters gravitationally in halos around galaxies and in filaments of the cosmic web. We know that it does not emit, absorb, or reflect light. We know that it does not form compact objects like stars or black holes. Because if it did, we would be able to detect those objects through their gravitational effects on passing starlight, a technique called microlensing. Beyond these constraints, the nature of dark matter is unknown. The leading theoretical candidate for decades has been the weakly interacting massive particle, or WIMP, a particle with a mass somewhere between a few and a few hundred times the mass of a proton, interacting with ordinary matter through the weak nuclear force and gravity. WIMPs are theoretically well motivated. They arise naturally in extensions of the standard model of particle physics, particularly supersymmetric theories, and they have a remarkable property. If they were produced in the hot early universe and froze out when the universe cooled, the relic abundance would match the observed dark matter density. This coincidence, sometimes called the WIMP miracle, made WIMPs the dominant paradigm in dark matter searches for decades. But experiments searching for WIMPs have so far found nothing. Underground laboratories on multiple continents using tanks of liquid xenon,
Germanium crystals, sodium iodide crystals, and other target materials have looked for the extremely rare events that would result from a WIMP scattering off an atomic nucleus. The sensitivity of these experiments has improved by many orders of magnitude over the last 2 decades.
The absence of a signal has not ruled out all WIMP scenarios, but it has eliminated much of the parameter space that seemed most natural, and has shifted the field toward considering a wider range of dark matter candidates. Axions, sterile neutrinos, primordial black holes, self-interacting dark matter, ultralight dark matter, fields oscillating coherently across macroscopic scales, and many others. The search continues, and the answer, when it comes, will have implications not only for cosmology but for fundamental physics. The evolution of galaxies over cosmic time is one of the most active areas of research in observational astronomy, and it is a story of transformation. The galaxies we see in the deep universe, the galaxies as they were 10 or 12 billion years ago, look very different from galaxies in the local universe. They are more irregular in shape, more active in star formation, smaller and less well organized over billions of years. Galaxies have grown through a process of hierarchical assembly. Smaller galaxies merge with larger ones. Gas is accreted from the surrounding intergalactic medium, and star formation gradually builds up the stellar mass. At the same time, feedback from supernovae and active galactic nuclei blows gas out of galaxies and heats the surrounding medium, regulating and eventually quenching star formation in the most massive systems. The most massive galaxies in the local universe, giant elliptical galaxies like M87 or the central dominant galaxies of clusters, are the accumulated products of many merger events. Their stars tend to be old, red and metal-rich, the products of an era of intense star formation in the early universe that has since shut down. They contain supermassive black holes whose masses correlate with the properties of the surrounding stellar bulge, a correlation that suggests the growth of the black hole and the growth of the galaxy are somehow connected through feedback processes whose details are still being worked out. Spiral galaxies like the Milky Way represent a different evolutionary path. They have ongoing star formation, a mixture of young blue stars and old red stars, a flattened disk maintained by rotation, and a central bar in many cases. Our own galaxy is classified as a barred spiral, with 2 major spiral arms, the Perseus arm and the Norma arm, and several minor ones, including the Orion arm where our solar system resides. The Milky Way has grown through mergers in its history, and it will continue to grow. In approximately 4.5 billion years, it will merge with the Andromeda galaxy in an event that will unfold over hundreds of millions of years. A slow-motion collision in which the 2 galaxies interpenetrate, distort each other's shapes through tidal forces, stimulate intense bursts of star formation, and eventually coalesce into a single, larger, roughly elliptical system that astronomers have informally named Milkomeda. The merger will not be violent in the sense of collisions between solid objects. Stars are so widely separated compared to their own sizes that the probability of 2 stars actually colliding during the merger is negligible. The solar system will be gravitationally disrupted, tossed onto a different orbit within the merged galaxy, but is unlikely to be destroyed. The sun will continue to shine, the planets will continue to orbit. What will change is the night sky. The familiar patterns of stars will be scrambled over millions of years as the merger proceeds, and the sky will be dominated by the glow of new stars being born in the burst of star formation triggered by the collision. The center of the merged galaxy, where 2 supermassive black holes will orbit each other and eventually merge, producing the most powerful gravitational wave event in the local universe in billions of years, will blaze with activity. But all of that lies
billions of years in the future.
For now, the Milky Way is a relatively quiet, middle-aged spiral galaxy, and the solar system occupies a fortunate position within it, far enough from the turbulent, radiation-intense galactic center to avoid the hazards of proximity to Sagittarius A and the dense stellar population of the central bulge, and far enough from the outer edge of the disk to be surrounded by stars of sufficient metallicity to have formed planets with the chemistry necessary for life. The question of which environments in a galaxy are most hospitable to the development of life, the galactic habitable zone, is a subject of active investigation. Near the galactic center, the intense radiation environment, the high density of supernovae, and the perturbations from close stellar encounters may make the sustained stability needed for the development of complex life difficult to achieve. In the outer regions of a galaxy's disk, the low metallicity, the scarcity of elements heavier than helium, which are necessary for forming rocky planets and for the biochemistry of life as we know it, may be a limiting factor. The intermediate regions of a spiral galaxy's disk, far enough from the center to avoid its hazards, but rich enough in heavy elements to form rocky planets, may be the most favorable environments. The solar system sits within this intermediate zone. The detection of biosignatures in the atmospheres of exoplanets, chemical compounds that could not be maintained in the abundance observed without an ongoing biological process, is one of the primary scientific goals of current and planned space telescope missions. The James Webb Space Telescope, launched at the end of 2021, has already begun to characterize the atmospheres of exoplanets, detecting carbon dioxide, methane, and water vapor in planets ranging from hot Jupiters to sub-Neptunes. Whether it will be able to detect oxygen or ozone in the atmosphere of a genuinely Earth-like planet around a nearby star is uncertain. The planet would need to be unusually close to a nearby star, and the observations would require hundreds of hours of telescope time, but it is at least possible in principle. Future missions currently in development include large space-based direct imaging telescopes capable of blocking the light of a star and capturing the faint reflected light of an Earth-sized planet in its habitable zone, allowing the spectrum of that light to be analyzed for atmospheric biosignatures. This is one of the most technically challenging observational goals in the history of astronomy, but it is one that may be achievable within the coming decades. If it succeeds, if we detect in the spectrum of a planet's atmosphere the unambiguous signature of biology, it will be one of the most consequential discoveries in the history of science. It will transform not just astronomy, but philosophy, religion, and our understanding of what we are and where we fit in the universe. The Fermi paradox, the question Enrico Fermi supposedly posed at a lunchtime conversation at Los Alamos in 1950, of where all the extraterrestrial civilizations are if they should be so plentiful, has attracted enormous attention and generated a vast literature of proposed resolutions. The paradox rests on a simple argument. The universe is old. Technological civilizations have had billions of years to develop, and even at speeds far below the speed of light, a sufficiently motivated civilization could spread throughout the galaxy in tens of millions of years, a geological eye blink, compared to the age of the Milky Way. And yet we see no evidence of any such civilization. No radio signals from other worlds, no megastructures in nearby star systems, no spacecraft from other civilizations anywhere in the solar system. Silence. The proposed resolutions to the Fermi paradox are numerous and range from the mundane to the exotic. Perhaps technological civilizations are simply very rare. The combination of a habitable planet, the origin of life, the development of complex multicellular life, the emergence of intelligence, the development of technology, and the survival of that technology long enough to produce detectable signals is so improbable that we may be among the first such civilizations in the Milky Way. This resolution invokes what is sometimes called the Great Filter. Some step in the sequence from simple chemistry to technological civilization is so difficult that virtually no planets pass through it. If the great filter lies behind us, if it is a step we have already passed, that is reassuring. If it lies ahead, it suggests that civilizations like ours rarely survive past a certain point of development. Perhaps civilizations do not attempt to communicate across interstellar distances for reasons we cannot currently anticipate. Perhaps they have communication technologies that bear no resemblance to radio waves. Perhaps they have recognized that the universe is large enough that contact between civilizations separated by thousands of light years is not practically achievable on any meaningful time scale. Perhaps they exist in forms post-biological, for instance, or operating on timescales very different from our own, that leave no signatures we would recognize as intentional. Perhaps they are there, and we are simply not looking in the right places with the right instruments. The search for extraterrestrial intelligence is still a young science, using a small fraction of the telescope time that would be needed for a comprehensive survey. What is certain is that the question matters. It matters for practical reasons. Understanding whether intelligent life is common or rare would tell us a great deal about the probability of our own long-term survival. It matters for philosophical reasons. The answer would tell us whether the capacity for thought and wonder is a cosmically significant phenomenon or a local accident. And it matters for the scientific program of understanding the universe as a whole. Because a universe that has produced intelligence many times and that contains civilizations that have understood their own history and structure is a fundamentally different kind of thing from a universe in which awareness has arisen only once, briefly on the surface of a small planet in an unremarkable galaxy. The universe does not, as far as we can determine, care about this question. It proceeds with its processes of expansion and cooling, of gravity pulling matter together and dark energy pushing space apart, of stars being born and dying, of galaxies assembling and eventually fading, regardless of whether any entity within it is watching and wondering. The indifference of the cosmos to our existence is not hostile. It is simply a consequence of the fact that the laws of physics do not require awareness to operate. Gravity curves space-time whether or not there is anything to observe the curvature. Nuclear fusion ignites inside stars in molecular clouds that have never been visited by any telescope and may never be. The cosmic microwave background fills the observable universe with its ancient light whether or not any receiver intercepts it, and yet awareness has arisen. We are here asking these questions. The matter of the universe has, in at least one place, arranged itself into a configuration capable of constructing instruments sensitive enough to detect ripples in space-time, 1,000th the diameter of a proton, and then of interpreting those ripples as the merger of two black holes more than 1 billion light-years away. That process, the self-examination of the cosmos through the medium of biological intelligence, is itself a phenomenon of the universe, part of its story, as much as the formation of the first stars or the assembly of the first galaxy clusters. What the story means, whether it has a meaning in any deep sense, is not a question that science can answer. Science can describe what the universe is and how it works. It can measure the curvature of space-time, the temperature of the microwave background, the distribution of dark matter, the rate of cosmic expansion. It can trace the history of the universe from the first fractions of a second to the far future. What it cannot do is tell us why any of this exists rather than nothing, whether the universe's fundamental constants, the strength of gravity, the charge of the electron, the mass of the proton, are contingent facts that happen to be suitable for life, or necessary facts that could not be otherwise, or chosen facts selected by some process we do not understand. These are questions that sit at the boundary of physics and philosophy, and different thinkers draw that boundary in different places. Some physicists argue that the fine-tuning of the fundamental constants, the fact that small changes in their values would produce a universe in which stars could not form, or atoms could not be stable, or the chemistry of life would be impossible, is evidence for a multiverse in which many values of the constants are realized in different regions, and we find ourselves in a region where they permit life simply because we could not exist in any other kind of region. This is called the anthropic principle. Others argue that the apparent fine-tuning will eventually be explained by a deeper theory that derives the constants from first principles, the way general relativity derives the geometry of space-time from a small set of axioms. Still others argue that the question itself may be malformed, that asking why the constants have the values they do assumes a framework that does not exist. These debates are not likely to be resolved soon. They may not be resolvable with any instruments or mathematics currently conceivable. But the fact that they are being asked, that the universe has produced a species that asks why it exists and what it means, is a fact about the universe that will not go away. It is woven into the story of what the cosmos has become in the 13.8 billion years since the moment when everything began. The universe is immeasurably large, inconceivably old, and still mostly unknown. We have mapped a fraction of what exists, interpreted what we have mapped with theories that we know are incomplete, and arrived at answers that have raised more questions than they have settled. This is not a failure. It is the normal condition of genuine inquiry. And the answers that have already arrived, the discovery of the cosmic web, the detection of gravitational waves, the imaging of a black hole's shadow, the first measurements of an exoplanet's atmosphere, the precise mapping of the oldest light in the universe. These are among the greatest achievements in the history of human thought. We began with a number, and we end with an open question. Not because the questions have defeated us, but because each answered question has revealed a more interesting and more precisely formulated question behind it. The universe offers this in abundance. The deeper you look, the more there is to see. There is a hierarchy of distance measurement in astronomy that is sometimes called the cosmic distance ladder, and it is one of the most ingenious achievements of observational science. The problem it solves is simple to state and enormously difficult to address. Space does not come with rulers attached. When you look at a star or a galaxy, you cannot immediately tell whether it is nearby and faint or distant and bright. The two are observationally indistinguishable without additional information. The history of astronomy is, to a considerable degree, the history of developing methods to obtain that additional information, to determine how far away things are. The first rung of the ladder is trigonometric parallax, which works for nearby stars. As the Earth orbits the Sun, stars shift slightly against the more distant background. The amount of shift depends on the star's distance. Closer stars shift more distant stars shift less. By measuring this shift with sufficient precision, the distance to a star can be calculated from simple geometry. The Hipparcos satellite, launched in 1989, measured the parallaxes of more than 100,000 stars. The Gaia mission, launched in 2013, has measured parallaxes for more than 1 billion stars with an accuracy that surpasses Hipparcos by a factor of roughly 100. Gaia's catalog has transformed our understanding of the three-dimensional structure of the Milky Way, mapping the positions and motions of a significant fraction of the galaxy's stars with unprecedented precision. Parallax works out to distances of a few thousand light years. Beyond that, the shifts are too small to measure, even with Gaia. The next rungs of the ladder involve standard candles, objects whose intrinsic luminosity is known or can be inferred, so that the distance follows from comparing intrinsic and apparent brightness. Sepheid variable stars, which pulsate with a period that correlates reliably with their luminosity, were used by Henrietta Swan-Leavitt to establish the distance scale to the Magellanic Clouds in 1912, one of the foundational discoveries of 20th century astronomy,
performed at a time when women at observatories were hired as computers to perform numerical calculations rather than as scientists.
Leavitt's discovery enabled Hubble to use Cepheids in the Andromeda Nebula to demonstrate that it was far outside the Milky Way, settling the great debate about the scale of the universe. Cepheids extend the distance ladder to tens of millions of light years, type Ia supernovae, which have a roughly standard peak luminosity and are visible across billions of light years, extended further still. The supernovae measurements of 1998 that revealed the accelerating expansion of the universe were based on this rung of the ladder. And each transition from one rung to the next introduces calibration uncertainties that accumulate the Hubble constant tension. The discrepancy between its measured value from local distance indicators and its inferred value from the cosmic microwave background partly reflects the difficulty of calibrating each rung correctly. Recent improvements have, if anything, sharpened the tension rather than resolving it, suggesting that the discrepancy may be real rather than methodological, that something in the standard cosmological model may be wrong. The possibility that the standard cosmological model requires revision is not alarming. It is the normal state of a maturing science. Models are refined when they fail to match observations, and the refinements sometimes reveal entirely new physics. The discovery of dark energy was itself a revision of the standard model. The original standard model had no accelerating expansion, no cosmological constant, no dark energy. The revision required to accommodate the supernova observations changed our picture of the universe dramatically. A further revision, perhaps involving a component of dark energy that evolves over time, or a modification of general relativity on cosmological scales, or something else entirely, would be equally significant. The standard model of particle physics, which describes the elementary particles and forces, except gravity with extraordinary precision, also has known limitations and tensions. It contains no dark matter candidate. It does not explain the matter-antimatter asymmetry, the reason why the Big Bang produced more matter than antimatter, leaving a residual of ordinary matter from which everything we see is made. It does not account for the masses of neutrinos, which were assumed to be zero in the original formulation, but are now known to be small but non-zero. The hierarchy problem, the question of why gravity is so much weaker than the other fundamental forces, which corresponds to asking why the Higgs boson mass is so much smaller than the Planck mass, remains unresolved. And the deepest problem of all, quantum mechanics and general relativity, the two most successful physical theories ever developed, are mathematically incompatible in the regime of extreme density and curvature, where both should apply simultaneously inside black holes and at the moment of the Big Bang. A theory of quantum gravity, which would unify general relativity and quantum mechanics into a single consistent framework, is the central unsolved problem in theoretical physics. String theory, loop quantum gravity, and several other approaches have been developed to address this problem, each with distinctive predictions and each with serious unresolved issues. String theory requires additional dimensions of space beyond the three we observe, dimensions that would be curled up at scales far smaller than any current experiment can probe. Loop quantum gravity proposes that space-time itself is quantized, that there is a minimum unit of length, the Planck length, approximately 10 to the power of negative 35 meters, below which the concept of distance loses meaning. Whether either of these frameworks, or some other approach not yet conceived, will eventually provide a consistent theory of quantum gravity is unknown. The problem may require concepts that do not yet exist in human thought. The Milky Way's central supermassive black hole, Sagittarius A, was directly imaged by the Event Horizon Telescope in 2022, 3 years after the collaboration's first image of M87's central black hole. The two images together, allow a comparison of black holes across 6 orders of magnitude in mass. Both images show the predicted photon ring, the ring of light produced by photons orbiting near the black hole before escaping, and both show a dark shadow consistent with the prediction of general relativity. The agreement between theory and observation is striking. General relativity developed by Einstein over a century ago without any knowledge of black holes has passed every test we have been able to devise, including tests in the most extreme gravitational environments accessible to observation. Whether it will continue to pass tests at scales and energies beyond those currently achievable, including the scales where quantum gravity becomes relevant, remains a central open question in fundamental physics. The interstellar medium, the gas and dust between the stars of the Milky Way, is far from the featureless emptiness it might appear to be. It is structured across many scales and encompasses an extraordinary diversity of physical conditions. In the hot, diffuse coronal phase, the gas heated to millions of degrees by supernova explosions. Hydrogen exists as a fully ionized plasma so tenuous that a cubic centimeter contains only a fraction of an atom. In the warm neutral medium, hydrogen exists as neutral atoms at temperatures of thousands of degrees. In the cold neutral medium, temperatures drop to a few tenths of degrees Kelvin, and the hydrogen density increases significantly. In molecular clouds, temperatures drop further, and hydrogen combines into molecular form. And in the densest cores of those clouds, the Bok globules, temperatures approach within a few degrees of absolute zero, and densities reach billions of molecules per cubic centimeter. The interstellar medium is also a site of complex chemistry. More than 200 molecules have been detected in interstellar space by radioastronomy, ranging from simple diatomics like molecular hydrogen and carbon monoxide to long organic chains containing a dozen or more atoms, including polycyclic aromatic hydrocarbons whose infrared emission features are ubiquitous in the spectra of galaxies. Amino acids and other prebiotic molecules have been detected in meteorites, which are samples of the early solar system, and in interstellar clouds. Although the detection of amino acids directly in the gas phase of the interstellar medium remains uncertain. The chemistry of the interstellar medium is driven partly by ultraviolet radiation from stars, which dissociates molecules and ionizes atoms, and partly by cosmic rays, which penetrate deep into molecular clouds where ultraviolet light cannot reach and drive ion-molecule reactions in the dark interior. The elements produced in stellar interiors and scattered into the interstellar medium by supernovae and stellar winds gradually increase in abundance over cosmic time. The first stars, the so-called population-free stars that formed from the pristine hydrogen and helium of the Big Bang, contained essentially no elements heavier than lithium. They lived fast and died violently, enriching the interstellar medium with the products of their nuclear burning and seeding the next generation of star formation with a richer chemical palette. Each subsequent generation of stars was born from gas more enriched in heavy elements than the last. The Sun, which formed approximately 4.5 billion years ago, is a third generation or later star. It formed from gas that had already been processed through multiple generations of stellar evolution. Its metallicity, the total abundance of elements heavier than helium, is roughly twice the galactic average, suggesting that it formed in an unusually enriched region of the galaxy. The planets of the solar system carry the chemical signature of the interstellar medium from which they formed. The carbonaceous chondrite meteorites, among the most primitive objects in the solar system, remnants of the material from which the planets assembled, contain a rich inventory of organic compounds, amino acids, nucleobases, sugars, and many other biologically relevant molecules. These compounds did not form on Earth. They were delivered from space and existed in the pre-solar nebula before the solar system formed. Whether they played a role in the origin of life on Earth
whether some fraction of the organic inventory of the early Earth was delivered by meteorites and comets rather than synthesized on the surface is an active area of research.
The answer has implications for the origin of life and for the likelihood of life arising elsewhere. If life depends on organic molecules that can only be synthesized in specific environments, life is likely to be rare. If those molecules are delivered universally by the same processes of stellar nucleosynthesis and interstellar chemistry that operate throughout the galaxy, the raw ingredients for life may be widely available. In the outermost reaches of our solar system, far beyond the orbit of Neptune, lies a vast spherical cloud of icy bodies called the Oort cloud. The Oort cloud is thought to extend from roughly 2,000 to potentially 100,000 astronomical units from the Sun so far that objects within it are only marginally gravitationally bound to the solar system. The occasional perturbation from a passing star or the tidal force of the Milky Way's gravitational field can nudge an Oort cloud object onto a trajectory that carries it inward, into the inner solar system, where solar radiation and heating sublimate its ices and it becomes visible as a long-period comet. Comets carry samples of the material from which the solar system formed, preserved in the cold of the outer solar system for billions of years. They also carry organic molecules and, in some cases, amino acids and other prebiotic compounds. The impact of comets on the early Earth. During the period of heavy bombardment approximately 4 billion years ago may have delivered a significant fraction of the Earth's water and organic inventory. The outer solar system is, in some ways, as alien and unknown as the deep cosmos. The Kuiper Belt, the region of icy bodies extending from the orbit of Neptune to about 50 astronomical units, was only confirmed to exist in 1992, when the first Kuiper Belt object beyond Pluto was discovered. We now know that thousands of such objects inhabit the Kuiper Belt, including several large bodies, Eris, Makemake, Haumea, and Gonggong among them, that rival Pluto in size. Beyond the Kuiper Belt, the even more distant trans-Neptunian region may contain a planet several times the mass of Earth, on a highly elongated orbit that would take it hundreds to thousands of astronomical units from the Sun at its most distant point. This hypothetical body, sometimes called Planet 9, has not been directly observed, but its gravitational influence has been inferred from the clustered orbital properties of a group of distant trans-Neptunian objects. Whether it exists, and what it would mean for our understanding of the solar system's formation and history if it does, is one of the more tantalizing open questions in planetary science. The systematic exploration of our own solar system through spacecraft, rovers, orbiters, and landers has revealed a diversity of worlds that continues to surprise. Mars, once thought to be a dead, dry desert, shows evidence of abundant liquid water in its past. Ancient riverbeds, lake deposits, and hydrated minerals in its rocks. Titan has active weather, a hydrological cycle driven by methane rather than water, and a subsurface ocean of liquid water beneath its icy crust. Europa's ocean contains more liquid water than all of Earth's oceans combined, maintained by tidal heating from Jupiter's gravity. Enceladus erupts geysers of water vapor containing organic molecules and hydrogen from a subsurface ocean in contact with a rocky seafloor, conditions potentially similar to the hydrothermal vents in Earth's deep oceans where entire ecosystems flourish without sunlight. These are all places within a few hours to years of light travel time from Earth. They are, in the context of the universe, essentially in our backyard. And they contain liquid water, organic chemistry, and energy sources that support life on Earth. The question of whether life has arisen in any of these environments is not purely hypothetical. It is a question that may be answerable within the coming decades, with missions already planned or in development. The Europa Clipper, launched in 2024, will study Europa in unprecedented detail, assessing its habitability and searching for evidence of a subsurface ocean in direct contact with the seafloor. A future lander on Europa, or a probe deployed through the ice into the ocean below, could potentially detect biosignatures directly. What we find in our own solar system will inform what we expect to find elsewhere. If life exists on Europa or Enceladus, if it arose independently on bodies within a single solar system, the implication is that the origin of life is not a singular accident, but a robust process that occurs wherever the conditions are suitable. In that case, life should be common throughout the galaxy. If life exists nowhere else in the solar system, despite the presence of liquid water and organic chemistry on multiple worlds, the implication is more ambiguous. Either the conditions in our solar system are insufficient, or the origin of life requires something rare that we have not yet identified. Either outcome would be of extraordinary scientific significance. The universe has given us more questions than answers, and it shows every indication of continuing to do so. The more precisely we can measure, the more anomalies we find, the more structures we map, the more unexpected patterns emerge. The more carefully we listen, the more signals we detect that require explanation. This is not a sign of failure. It is a sign that we are doing science correctly, that our instruments and methods have become good enough to find the things that do not fit the models, the discrepancies and anomalies and surprises that drive genuine progress. We live in a remarkable moment in the history of this inquiry. The tools available to astronomers and cosmologists today, space telescopes, gravitational wave detectors, neutrino observatories, radio arrays, cosmic ray detectors, particle accelerators, provide a view of the cosmos that would have been unimaginable a century ago. The data being collected, processed, and interpreted at this moment exceeds in volume and precision everything collected in all of prior human history. And the questions being asked about the nature of dark matter and dark energy, about the geometry and topology of space, about the possibility of other universes, about the conditions for life, about the fate of the cosmos, are among the deepest questions that have ever been formulated. Whatever answers arrive in the coming decades, from the next generation of gravitational wave detectors, from the extremely large telescope on the Atacama Desert, from future missions to the icy moons of Jupiter and Saturn, from surveys of the microwave background with unprecedented resolution, from direct imaging of Earth-like exoplanets, they will not end the inquiry, they will deepen it. Because the universe, as we have seen, is patient with our curiosity, and what it has to reveal appears to be, in the most literal sense of the word, inexhaustible. There is a perspective that astronomy uniquely enables, and that few other disciplines can provide with the same force, the perspective of deep time. Human experience is calibrated to timescales of seconds, hours, years, and at the outside a human lifetime of decades. Our intuitions about cause and effect, about change and stability, about beginning and ending are all formed within that narrow temporal window. But the universe operates on timescales that make a human lifetime unmeasurable. Not small, but literally unmeasurable by any instrument sensitive enough to detect the difference between the beginning and the end. The sun has been burning for 4.5 billion years. In that time, it has not changed noticeably from one year to the next, or from one century to the next. From the outside, it looks the same as it did when the first single-celled organisms appeared in Earth's oceans. It will look essentially the same for another 5 billion years. The changes it is undergoing, the slow increase in luminosity as the hydrogen in its core is gradually depleted and the core contracts and heats, operate on timescales completely inaccessible to human experience, detectable only through the fossil record,
and through the internal consistency of stellar physics, the Milky Way has been rotating for billions of years. Its outermost stars complete one orbit in several billion years. The spiral arms, which are not physical structures but density waves propagating through the disk, rotate at a different rate than the stars so that any given star passes through a spiral arm multiple times over its lifetime. The Sun has orbited the galactic center roughly 20 times since it formed, each orbit taking approximately 225 million years, a galactic year. The last galactic year ended approximately when the dinosaurs were at their peak diversity on Earth. The one before that, when complex animal life was just emerging from the sea. In the scale of geological time, human civilization is a recent flash. In the scale of stellar time, all of recorded human history is negligible. In the scale of cosmic time, the entire age of the solar system represents roughly 1/3 of the universe's history. And the future time available, the trillions of years during which stars will continue to burn, during which the cosmic web will continue to evolve, during which whatever is going to happen in the universe is going to happen, is so much longer than the past that we are, in the most profound sense, at the very beginning. This is simultaneously humbling and extraordinary. Humbling because it places human existence at an almost invisibly small point in the universe's temporal expanse. Extraordinary because it means that the universe is not winding down. It is still forming, still assembling structures, still igniting stars, still perhaps producing environments where chemistry organizes itself into the complexity that leads eventually and unpredictably to awareness and inquiry. The universe's story is not mostly past, it is mostly future. And whatever that future contains, whatever structures form and dissolve, whatever stars rise and fall, whatever processes of self-organization occur in the enormous expanse of time that lies ahead, we are at this moment very near the opening chapter. To look up at the night sky with this awareness is to experience something that has no adequate name in any language. The sense of standing at the edge of an incomprehensibly vast ocean of time and space, knowing that the light reaching your eyes is ancient, knowing that the structures it reveals have been assembling for billions of years and will continue assembling for billions more, knowing that the atoms in your body were forged in stars that no longer exist and will eventually be incorporated into structures that do not yet exist, knowing that the capacity for awareness that allows you to register all of this is itself a product of the same processes, gravity, nuclear physics, chemistry, evolution that produced everything else. The universe is not indifferent to us in the sense of being hostile. It is simply much larger and older and more complex than our experience of it. We are inside it looking outward and backward, with instruments built from its own materials and theories constructed from its own regularities. We are, in some meaningful sense, the universe examining itself, and what it has found so far is that it is worth examining. The paradoxes of the infinite universe, if it is infinite, are not paradoxes that admit simple resolution. An infinite universe containing an infinite number of galaxies and an infinite number of planets and an infinite number of chances for something like us to arise is a universe in which everything that can happen does happen somewhere. That is not a comforting or a terrifying thought. It is simply a strange one, at the boundary of what the human mind can hold. And the question of whether the universe is in fact infinite, and what infinity would mean if it were, and whether there is a difference between a universe that is infinite and a universe that is merely unimaginably large. These are questions that connect physics, mathematics, and philosophy in ways that have not yet been fully untangled. What we can say with confidence is this: the universe is larger than we can see, older than we can fully comprehend, and more varied in its contents than we have yet imagined. It contains structures on every scale, from the Planck length to the scale of the observable horizon. It evolves on timescales from the Planck time to the heat death of everything.
It is held together by four forces whose ultimate unification into a single framework remains the unsolved problem of theoretical physics. And in at least one unremarkable corner of it, around one unremarkable star in one unremarkable galaxy, it has produced creatures who have spent the last few centuries determining all of the above, and who will spend the next few centuries learning what they got wrong. The universe has no obligation to be comprehensible. The fact that it is to the degree that it is the most surprising thing about it.